Hello, students. I am still sick, and because I'm still sick, I will not be on campus today to give a lecture in the classroom. So I'm going to record this lecture for you to watch, and hopefully I will be back on Monday. I'm planning on being back on Monday. So I will see you then. But in the meantime, I want to talk to you about our fossil fuel and climate change lecture. So today we're going to have this agenda. So first, we're going to talk about some syllabus reminders. And I'll re-emphasize this on Monday when we meet again. Then we're going to talk about what is energy and how is energy currently used. Then we're going to talk about types of energy that currently exist. And then we'll talk about what coal is exactly, how it's extracted, and the same for natural gas. And then we'll finish by talking about energy and the environment overall. So some syllabus reminders. So I've tried to be really lenient over these first 4 weeks, especially with regard to cell phones, but it has definitely become a problem in our classroom where um, basically everyone is on their phone all of the time. And not only is that disrespectful for the person that's giving the talk in class, but it's also disrespectful to yourself because you're here to learn, and you can't really learn if you're playing on your phone, scrolling through Twitter, looking at videos and things like that, right? So in the syllabus, I do have a statement on cell phones, and I was trying to be, again, lenient, so make sure that to really see if you all had the ability to actually control your phone usage in class. And over the 4 weeks, I realized that's not possible, right? So I will be implementing the syllabus statement from here on out. So it's fine to use a laptop in class to take notes, but don't use your laptop, cell phone, or other devices unless we need it, right? So if you're taking notes, that's fine, that's one thing, but don't have your phone out unless we're doing some sort of survey on Poll Everywhere or some other reason that I ask you to pull your phone out. So if you don't have a laptop, we can get a laptop. Each individual student has access to laptops from the library. So there really is no excuse to not have a laptop available to you in class, right? So you can just go right before class and pick up a laptop from the library and then return it right after. So if you really have a reason to be monitoring your cell phone, such as that you're expecting to receive an important update from somebody that's hurt, or anything like that, please let me know. And just let me know really quick, like, hey, I'm going to have my phone out because some really compelling reason, right? And if you do that, then I'll make that exception for you. But otherwise, cell phones should be put away at the start of class from here on, right? I will tell you when we need to pull them out, when we should pull them out to use them for any kind of activity or any kind of questioning. But they should be put away either in your backpack or just face down on your desk. So if you're on your phone, you are not paying attention to what I am saying in class or to what your classmates are also saying when we do group discussion work, right? So this means you're not actively being present in the classroom itself. So because of that, if you are caught using your phones when I don't have an activity that requires it, I will start marking you absent from class for the day. You need to be present. It's an hour and 15 minutes, and you can be present for that long. You'll get so much more out of the class if you do these things, right? So this also correlates to earbuds, right? So I don't want to see any earbuds in your ears anymore, on your head, face, neck, anywhere on your body. As soon as you come to class, those should be put away in your backpacks. And I will be, again, marking people absent if I see these phones being used when they're not allowed to be used during class. So keep that in mind when you come to class on Monday. Also, I wanted to say that you're coming to, this is college, right? So you're coming to these classes, you're paying to be in these classes. So you should want to be focused and you should want to learn while you're in these classes, not just my class, but anybody's class, right? So do yourself a service and come and pay attention while you're in class, right? All right, I'll quit harping on that. So what do we use energy for in the United States? So this is two graphics. So you can see the one here on the left is from 2019 and the one on the right is from 2021. Mostly the percentages have stayed the same over that 2.5 year time period, right? So we mostly use our energy in the US for transportation. Second most is industrial, third most is residential, and fourth is commercial. And that stayed the same over this time period, right? And so we use about 73.5 quadrillion BTUs of energy, and BTUs is the unit that we measure energy in. So that's about how much we use in the United States, right? So transportation is number one, but you can see how close industrial energy usage is to transportation. And so thinking about transportation and thinking about industrial uses, we can start to think about areas where we might want to cut our energy uses in the United States. So then where does our energy come from? So this is the same layout. On the left is 2019 data, and on the right is 2021 data. So you can see that mostly our energy in the United States comes from petroleum, followed very closely behind by natural gas. Then we have our renewable energy, then we have our coal, then we have our nuclear electric power at the bottom. And you can see here that over this time period, those percentages have roughly remained the same overall. We can see that the petroleum dropped 1% and renewable energy increased 1%. So that's a good sign for our renewable energy futures. So if we want to compare, we can look at this map of the United States here, and we can start to look at like North Carolina, for instance. So we clicked on North Carolina, and so this has some quick facts about North Carolina. It has consumption by source, consumption by sector, how we produce our energy, our electricity, and our prices, right? So if we look at production, we can see that nuclear power is our most commonly produced form of energy in North Carolina, followed by non-combustible renewables and wood and waste burning, right? And so then you can look at consumption by sector, and you can see that these are roughly basically all the same percentages, right? So our residential, commercial, industrial, and transportation are about the same in that 20% range, right? So we can go back and compare that to, say, California, right? So click on California, it gets those quick facts. For their consumption, you can see that their transportation is in the 34% range. So, about 10% more than we are, about 5 to 10% more than we are in North Carolina. And then commercial is a lot less at about 19%. For their production, you can see that their production is slightly headed out by non-combustible renewables, followed by crude oil. They have hardly any nuclear power, right? So you can start to see how the energy grid around the United States has changed depending on which state you are in. So I can post the link or I'll post this whole entire PowerPoint so you can play around on that website to get more information about any state that you might be interested in. So when we're talking about energy, we need to talk about this EROEI ratio, right? So this is the energy return on energy investment. And this ratio allows us to compare the amount of energy that we get from any source that we get energy from to the amount we must expend to obtain, process, and ship it and get it to the consumer, right? So when we have we look at these common types of energy sources here, we have coal, nuclear gas, nuclear power, wind, hydroelectric, and solar power, right? So when we look at this list, we need to think about like which is best, right? Which is the best when we're talking about this energy return on energy invested, right? So if we look, the first number that's listed after each of these types of energy, and there's a second number, right? So it's a ratio. The first the first number, so for coal 18, that's the amount of energy that we've returned, right? That's the amount of energy we get from the source. And then the second number, which is 1, is the amount that we've invested. So for each one unit of energy that we invest in coal, we get 18 units of energy out. So you can see that coal is really high up in this list. Natural gas, we get about 7-to-1 ratio. Nuclear power is 5-to-1. Wind is 20-to-1, so slightly better. Hydroelectric is 40-to-1. And then solar is around 0.2-to-1, right? So we can start to see that why coal makes such a good sense monetarily for the energy that we invest to get it out and the energy we get from burning it, right? So coal makes really good sense that way. Wind makes really good sense that way. And so does hydroelectric, right? But we need to think about more than just the energy to extract it. We need to start thinking about the environment itself. So this is a figure here from the U.S. Energy Information Administration. And this just shows how the use of coal has decreased over time. But the legacy of that coal still remains, right? So we've decreased our usage of it, but we are still producing it, and we are still exporting it and either using it in America or exporting it other places, right? So the blue line is our coal production line. You can see that production has decreased over time. The green line is our coal consumption line. So the consumption of it has decreased over time. And the brownish color line is our net import. So you can see that's below 0. So we're not importing anything, but we are exporting some, right? So coal, the use of coal, even though it is really good, has that really good energy return on energy investment, we have started to decrease our usage of it over time. So I have this poll everywhere, which we're not together, so we can't do it right now. So I just wanted to ask, what are the 4 things we need for coal to form, right? So we need heat. That's definite, right? Remember I talked about how we needed heat to make the coal form. We need a long time. We talked about 300 million years. We need pressure, so it needs to be squeezed together so we can form that coal block. And there needs to be some sort of plant matter present, right? And this needs to happen in an oxygen depleted environment. So C is the odd one out. So the correct answer here is A, B, D, and E, right? So again, here is how we have coal form. And lignite is the precursor to coal. It is a type of coal, but it doesn't have as much energy usage in it itself, right? So we have some kind of decaying plant matter here in the peat area. We have heat that's added to it over time. It gets hotter, warmer, and warmer. Then we have pressure forming on top of that decaying plant matter. And then as time increases, then we get the formation of that precursor coal of lignite. And then we get the coal itself. And then there's also multiple different types between the lignite and the final coal that we can extract. It's just not as efficient when we're trying to burn it for energy as the coal itself, right? So if you're interested in coal, I highly recommend looking that up. So for coal mining, we can do coal mining with surface mines or subsurface mining, right? So this is just a figure here that's showing the different types of subsurface mines and coal beds and how they brace up the mine itself so it doesn't just collapse in on itself. So subsurface mines are used to access the minerals and ore, including coal, that we need to get energy, right? So modern mining depends on really, really powerful machinery that goes in here and drills out these tunnels and then excavates and removes that coal and transports that material back to the surface, right? So subsurface mining is mining that happens underground. So surface mining would be the mining that happens at the surface level, right? So they would just dig like a big pit and keep going down in this pit, but they're always exposed to like the atmosphere, right? Surface mining is a lot safer form of mining for workers altogether, but it provides fewer jobs than the subsurface mining. And when we're talking about coal and jobs are like 2 things that go hand in hand, right? When we do the subsurface mining, the ecological impact is a lot larger than subsurface mining as well, right? And we have long-term surface damage that happens to the actual surface of the ground itself, and the safety with regard to these slurry impoundments are a major concern, right? So slurry is water that gets mixed with all of these chemicals and dirt that are being removed, and that slurry is really dangerous. There's an interesting story. I'll try to look it up. But there's a surface mine, I think it's in like Montana. It's this huge surface mine. And over time, once they stopped using it, because they dug it down so far that it actually got into the water table. So they've gotten to groundwater, but they were pumping it out when they were actively using the mine. So over time, that mine has been abandoned, right? And this is a surface mine, right? So it's a big pit. And so the water has increased in depth in this subsurface in this surface mine. And now all that water is toxic. And the mining company or the state forest service, I don't remember, someone pays somebody to stand out on that mine 24/7 to scare away migrating birds, because if they land in the water that's in that mine, just within a couple hours they will die from the toxicity of the water in that mine. So it's, again, that slurry and the water that interacts with what is being pulled out from these beds, these coal beds, is really dangerous, right? So it's really dangerous. So for subsurface mining, this creates more jobs and it creates less surface damage, but it's more dangerous because you're digging under the earth. You have to put these support beams in. There's a potential for collapse. There's a potential to be exposed to harmful materials. There's a potential of oxygen depletion. So there's all kinds of dangers. They also pump oxygen into some of these mines, and pure oxygen is very flammable. So there's problems with that as well, right? So with the subsurface mining, we also need to think about acid mine drainage and the leaching of toxins into the streams and groundwater, right? So we have acid mine drainage. We can damage not only our groundwater reserves, but once it gets into the groundwater, it can leach into our streams as well. So there's also, for surface mining, there's mountaintop removal. So you can see here, these two figures, you can see on the left, you can start to look at these coal seams that are running through this mountain. You can see that there was once a mountain forest. There's some streams that run down that mountain to a larger river below. And then there's a local community that exists. And so this up here in the top right is an actual picture of a mountaintop removal site. So here in the bottom, you can see that that coal seam is now exposed. They literally removed the mountain here. You can see that coal sludge impoundment. So that's what we're talking about with that slurry, that impoundment here. The overburden is dumped into the valley below, right? So anything extra is just dumped into the valley below. And then that is smothering those small streams that used to exist on this mountain itself. Then the runoff flows over that exposed dirt area, right? And it delivers silt and acidic sulfur compounds, the coal sludge from the ponds. It delivers all of that into the river that's adjacent, polluting the adjacent river. And now that the river no longer has a riparian zone that it can flood into, it's now flooding over to where that local community is. And that local community is then extirpated, right? So they can no longer live there. They're moved out, right? So it causes a lot of damage and a lot of far-reaching damage. So when we talk about coal, we also talk about coal ash. So coal ash contains a lot of different contaminants like mercury, cadmium, arsenic. All of those are really hot topics, and they're in water research today, and they're very, very dangerous to human life. So without properly managing the ash that exists from the burning of this coal, the contaminants, again, can easily pollute our surface waterways, our groundwater, the drinking water that we drink every day, as well as the air that's surrounding us, right? So I have here this information that 1 pound of coal can power 10 100-watt bulbs for an hour. So it's again pretty efficient at doing that, right? So you can see here the process of using coal for electricity. One, that the coal is sent to the furnace where it is burned to produce heat. You can see that that smokestack is then emitting sulfur particulates, mercury, arsenic, carbon dioxide, and things like that. So water is then heated in pipes from that burning of the coal, and then steam is produced and then it's funneled to this turbine, right? So then the turbine spins, and a magnet spins alongside a copper wire, and as that's spinning, it actually produces the electricity, right? So we're heating this coal, we're burning this coal to produce steam. That steam then turns a turbine, and that turbine then produces the electricity, right? So then the transformer is the last stage at the power plant. So this is the voltage is ramped up. So we're increasing the voltage, and then it's being sent out to the grid, right? So higher the voltage, the further that electricity can travel along our power lines. And transformers on the power lines step voltage down before it enters your home, right? So you don't want your house to like blow up because it has too much energy. So then there's the water that's made from the steam production. It's then cycled over to a storage tank here. And then there's cooling water that is brought in to the power plant that cools down that steam water. And that cooling water is taken from a nearby river. The water is then heated again as it's cooling the steamed water down. Then it's released back into the water, which is causing, again, another form of pollution, which is thermal pollution, right? So that water is superheated, it's entering the river and causing the temperature of the river to increase, right? So there's a lot that goes on with this coal production. And so the coal ash is what's left over from this burning process, right? So if you've ever burned a fire, you've seen ash in the bottom of your fire pit. So for coal ash, again, it has these toxic chemicals such as mercury, cadmium, and arsenic. And then that coal ash in the past was just left out on the surface or buried underground, and it's caused really bad problems for our drinking water. So this is a map that looks at major coal deposits around the world, and the recoverable coal at producing mines is about 20 years, right? So we have about 20 years. So the total recoverable coal is 332 years. And the top 5 countries and their share of the world coal reserves in as of 2017 were the United States at about 22% of the coal in the world, Russia at 15, Australia at 14, China at 13, and India at 10. And if you look here, you can see the different types of coal. So the darker blue is the anthracite coal, and the light the light brown is that lignite, so that less efficient type of coal, right? So then you might have heard the term of clean coal. So clean coal technology is a technology that minimizes the amount of pollution that's produced by coal, right? So some examples of this are when you burn coal, you can capture the gases and other emissions that happen out of that smokestack when the coal is burned itself, right? So doing some type of trapping of those gases and emissions, right? And we can either turn those gases into another form of energy or just trap them for other uses, right? So we can also chemically remove some of the toxins within the coal itself before it's burned. So like washing the coal, right? So we can try to do that. However, critics point out, and I agree with this, that these processes require more energy, right? So then they're going to lower that energy return on energy investment. And we're still going to produce toxic waste, right? There's still going to be toxins in the environment. So cleaning the coal probably isn't the best solution, right? It's probably going to be using some other form of energy. So I have some questions for you to think about when we're talking about mountaintop removal. So I'd like you to think about what is mountaintop removal? Again, how has mountaintop removal impacted human health? You've already answered these questions in your homework assignments, right? How has mountaintop removal impacted economic health? And how has mountaintop removal impacted ecosystem health? You're going to probably see these on our tests, right? So keep those in mind. So for surface mining, the mountaintop removal, I wanted to give you some facts about this. About 500 mountains are destroyed, and that's about 1 million acres, right? 1.5 million acres of Appalachian forest has already been destroyed. You can see this figure in the top, this poverty and strip mining in Appalachia. And you can see where a lot of that strip mining and mountaintop removal has occurred, right? So here in our homeland of the Appalachian Mountains, we have this problem happening. So we have loss of habitat and a loss of our carbon sink because we are in the mountains, we have all those trees, but again, with mountaintop removal, we just tear them all down. About 2,000 miles of Appalachian headwater streams are covered with the overburden, right? So covered with that that soil that is removed to get to the coal deposits. And again, soil really affects water quality and macroinvertebrate and aquatic habitat in a lot of variety of ways. For instance, when we have a lot of soil entering our stream, it starts to look muddy. So we've probably all seen a muddy stream. When the stream is muddy, sunlight isn't able to reach the bottom of the stream, so the stream bed. When sunlight isn't able to reach the stream bed, then our plant matter that grows within our stream environments are not able to photosynthesize, so they die. So then the macroinvertebrates, so the little bugs that eat those plant species, don't have a food source, so they die or go downstream. And then the fish no longer have anything to eat because they eat both plants and macroinvertebrates. And because of that, the fish also leave or they die, right? So just adding more of this overburden or the soil to the water itself is very detrimental to our ecosystem in the stream. So again, we have problems with water quality, like I just described. We have problems with flooding, like we showed in the picture earlier. We have fly rock that is added, those slurry impoundments that are happening along the stream beds, and we have loss of property value and losses from flooding, right? So the human component to this issue. So you can also see here this figure that shows you biodiversity hotspots, and you can see that in the Appalachian Mountains, that's really high. And when we add strip mining and mountaintop removal in those areas with biodiversity, we see a decrease in biodiversity overall. So very, very damaging. So don't we have regulations to protect the environment from this, right? Yes, the answer is yes, but they're very weak, right? There's always a loophole, and if you have enough money, you can find that loophole. So the Bush administration loophole in 2002 reclassified mining waste as permissible fill material under the Clean Water Act, right? So they're saying that this can be fill dirt that can be used anywhere. Well, like we talked about, anything that we put in the ground is going to leach into our groundwater, and our groundwater is eventually going to make it to our streams, and that's a really big problem. So coal companies are required to rehabilitate, so rehab the mined surface, but they're not required to return it to forest, right? So this surface area could be rehabilitated, but it's not forested. So we need to have stricter rules that say what rehab is for these mined areas, right? It needs to be returned as closely to possible to what it was previously. So again, these are some questions that you will definitely see again. What is coal ash? What kinds of risks to human health and the environment does coal ash pose? Why has coal ash become a problem? What have been some major coal ash incidents in the past? And how much is coal ash cleanup costing Duke Energy, specifically in North Carolina, and its customers? So since 2014, there have been at least 2 major coal ash spills here in North Carolina. So over the last, 8 years, In February 2014, Duke Energy spilled 39,000 tons of coal ash into the Dan River, right? So very, very, very problematic. In 2018, Hurricane Florence led to spills at Lee and Sutton power plants, and also very, very bad. So there's an interactive map that I recommend taking a look at. So this is coal ash site spills and their effects. And so you can look at each of these and see how far reaching those spills were. You can see this is the Dan River and how far that coal ash has gone, right? So again, you'll be able to click on that when I upload the PowerPoint. And then there's a link to a report here, which is investigative reporting that is very good. So the main issue with coal ash is that coal ash is dangerous, and it's a dangerous byproduct of burning coal that we need for energy, right? We have in the past, we're slowly moving away from it. But that coal ash is so dangerous because it contains those heavy metals, and those heavy metals are really hard to contain, and so is the coal ash itself, right? So there's storage lagoons, but those storage lagoons are known to seep those heavy metals into the aquifer, so our groundwater beneath our feet, as well as into surrounding rivers anytime it floods or we get hurricanes. Discharging some of this coal ash is allowed, but the question becomes, is Duke discharging too much of it into the stream? What is the amount that's okay that the stream can actually dissipate itself, right? What are these questions and what are these answers? What are the answers, right, to these questions? So this is a really cool figure. I'm not going to walk through it, but you can look at this on your own time. Basically, it's just walking through the issues with coal and how that hurts when given snapshot of an environment. So now we're going to talk about where does natural gas and oil come from. So you've seen this figure before. So before we talked about coal comes from plant material that's decaying. It's compressed with pressure and heat and given a long period of time, and we have those coal reserves that are formed. So for fossil fuels, we have marine organisms that die. They're then buried in that sediment. Again, they're in an oxygen depleted environment, so that slows down the decay of their body masses. As that sediment accumulates over top of them, the heat and pressure at a long period of time converts their body mass into oil and natural gas, right? And so the oil and natural gas move upward in some type of porous rock. So porous rock, just rock with small holes in it, until it's stopped by some dense rock. So it has fewer holes in it. And then we drill a hole and we tap those reserves, right? So we tap our natural gas, extract that natural gas first, then we tap that oil seam and we extract that oil. So there's two types of oil. There's conventional oil and unconventional oil. The first one, conventional oil, is very easily accessible. It's found in reserves, and it's extracted in a similar method to water, where we just dig a well and the pressure just pushes that oil up, right? So then there's unconventional oil. It's not very easily accessible. It's typically found in pore spaces of rocks. So you have a rock and it's in those individual pore spaces, and therefore it needs really advanced techniques to extract, right? So you can see here an example of a conventional gas well. So it's just pumping straight down. That gas is just coming right up. An unconventional well, you can see here it's going a lot deeper, and it's tapping into this oil and gas rich shale. So shale is a type of rock that has lots of pores in it. And so they're tapping into that. So conventional oil reserves contain oil that can be extracted by, again, those traditional pumping wells. Think your water well, right? The crude oil is, it consists of what we call hydrocarbons, which is hydrogen and carbon compounds together. And this is in a liquid form, right? Most of this crude oil is trapped in rock 0.2 to 5.5 miles below the surface itself. And then proven reserves are what we call the amount of fossil fuels that are economically feasible to extract using our current technology, right? So if you think about energy return on energy investment, the proven reserves are the amount of fossil fuels we can economically extract, right? So you can see here in this figure, the oil and natural gas between all of the countries. Middle East has an absolute ton. They have 49% of our oil and 51% of our natural gas. Eurasia has 32% of natural gas and 7% of oil. And you can see how that changes when you look at all the different countries. So there's also other reserves. So that last figure was showing you like landmass reserves, but there's also offshore and Arctic reserves that are out there. But what are the environmental impacts of developing offshore and Arctic reserves, right? So there's this World Wildlife story here that is very interesting that talks about how offshore oil will impact Arctic wildlife. So I highly recommend looking at that. But we can also see here that 87% of federal offshore acreages is off limits to development, right? So 87% is where we don't want any type of development happening offshore, right? So when we're talking about offshore, we're literally talking about offshore, right? So in the ocean, right? So you can see here, there's a couple areas that are open. So like in the Gulf Coast, we all remember the oil spill that happened with BP. And so that was in this area, very detrimental, right? So you can take a look at this map a little bit more on your own time. So when we think about those offshore drilling locations and we think about those areas that are outside, they're off limits, right? And this graphic was made in 2011, so it was a long time ago. But these are off limits, right? But then we think about new drilling leases that happened under different presidents. So you can see here, Bush opened up a couple areas around Alaska and here in the Gulf Coast. And then Obama still allowed that Gulf Coast, but got rid of the Alaska. There's one little tiny spot in Alaska here, and this little blip here in the North Atlantic. But then under Trump's presidency, opened up most of that area of basically all of our coastline in the United States was open to drilling under Trump's presidency. So this is where coastal states stand on offshore drilling. So the governor is in favor in blue states and the governor opposes in those orange states, right? So you can see where if we compare this map here under Trump's presidency to this map here, you can see that a lot of those states, especially along the Atlantic seaboard, are opposed to offshore drilling happening because we know what kind of problems happen, especially if we start to think back to the Gulf Coast and all of those oil spills that have happened. Again, so this is a conflict, right? So what do we do? Do we drill offshore? Do we not drill offshore? So unconventional reserves, we talk about those unconventional ones, so those ones that are harder to tap into. We talk about the shale oil. So again, shale is a geological type of rock. And then we can think about fracking. We've all heard of fracking. So what we call tight oil or shale oil is an oil that is trapped in impermeable rock deposits. So impermeable meaning not able to flow through, right? So the pores don't go all the way through the rock. So you have to actually tap into the rock itself in order to extract it. So again, this oil cannot be extracted using conventional methods. So fracking must be used instead, right? So deposits are often dispersed and buried thousands of feet below the surface. So you have to dig really big holes, drill really big holes, and we have to drill a lot of them because it's very dispersed. In 2014, about 1 million barrels of crude oil were recovered from the Bakken in North Dakota, and 7.4 billion barrels of shale oil, right? So they're extracting crude oil and shale oil from this one area in North Dakota. So for perspective, the U.S. consumed about 19 million barrels of oil daily in 2013. So this is just barely putting a dent in that we're consuming daily. So the Dakota Access Pipeline, which you might have all heard of, was built to start moving that tight oil from North Dakota to the customers that is us, right? But we'll talk about that in a second. So you can see this oil production from fracturing from 2000 to 2015. You can see how that's just spiked, right? So we're doing a lot of fracking in the United States. And you can also see here the number of wells for fracking that exist in the United States. So there's a video here called How Fracking Works. I would like you to all take your time to watch that video on your own time. But essentially what we see is that with fracking, they drill a hole, they inject high pressure water and sand and chemicals into the ground, right? So this is another slurry that's water, sand, and a bunch of different chemicals being injected into the ground at really high pressure, right? So we have this drilling rig, we dig this hole, and then we have this slurry being injected into the earth. And at that high pressure, it causes the fractures to form above and below the well itself. And that releases the trapped gas from that rock itself, right? So that's the basics of fracking, right? But once we have that slurry injected into the earth, we cannot get it all back out. And that slurry now has pore spaces that can move through to get into our drinking water aquifers, to our groundwater, and into our streams, right? So it's very dangerous. So if we think about that energy return on energy investment for crude oil versus the tight oil or the fracked oil, right? You can see that the conventional oil has a lot higher energy return on energy invested than that fracked oil, right? So it's not economically feasible to frack when you compare it to just getting traditional oil. So why do we do it, right? So there's a lot of fracking trade-offs that are listed here and some controversies in fracking that I'd like you to take your time to watch. And know that in areas such as this gentleman here, that the chemicals injected into the ground are flammable, and he actually is able to light his drinking water on fire, right? So it's really dangerous. So fracking is very, very detrimental to the environment. So another unconventional reserve is tar sands or oil sands. And Canada has the world's largest reserve of this unconventional heavy black oil, but that oil is trapped in sand or clay, and it's known again as tar sand or oil sand. So these tar sand deposits are mined by strip mining or open pit techniques, and the oil is extracted by underground heating, right? So they heat it and then the oil comes out. The deposits are estimated at 1.23 trillion barrels, but it's not economically feasible to extract them, right? So it takes a lot of energy to extract them, and we won't get that much energy back. So the tar sand extraction produces 3 to 4 times more greenhouse gases than conventional oil. And toxic compounds, again, have been found downstream of any of these mining sites, right? So the Trans-Alaska Pipeline delivers oil across Alaska, and the proposed Keystone XL pipeline was supposed to carry tar sands from these reserves in Canada all the way to Texas, but it was officially abandoned in June of 2021 because the people spoke up, and we spoke up enough and long enough to get that pipeline abandoned. So although there are large quantities of unconventional reserves that exist, the environmental cost of extracting them are really high, right? So the environmental costs are high for these unconventional oil sources, and the energy return on energy investment are really high. So that brings us to how much natural gas and oil is left, right? So you can see this figure here that there's a lot more left, specifically in the Middle East and here in Canada, especially if you think about those tar sands. But in like Mexico and the United States, we see this really small amount that's left. which brings us to this concept of peak oil. So peak oil is a very specific point in time when oil production will reach its peak, right? So when the production will be at its maximum. All countries currently have reached this point, and we have about 40 years of oil left before we have no more, right? So you can see the world peak happened right here, which was about 2010-ish, right? And so everything from here on out, we have reached the limit, the peak, the maximum that we will ever be able to extract, right? And so now we're extracting fewer and fewer gallons of oil, and that's causing us to start to think about other unconventional methods such as fracking or harvesting this tar sand in the future, right? So there are government subsidies on oil, and I have some quotes here from this report that is very interesting, so you should take a look at it. But conservative estimates put U.S. direct subsidies to the fossil fuel industry at $20.5 billion per year, with 20% currently allocated to coal and 80% to natural gas, right? So the U.S. is subsidizing the fossil fuel industry about $20 billion a year. Also have this quote here: a recent analysis published in Nature Energy found that continuing current fossil fuel subsidies would make it profitable to extract half of all the domestic oil reserves. This could increase the U.S. production of oil by 17 billion barrels over the next few decades, and emit about 6 billion tons of carbon dioxide, right? So these subsidies are paving the way to continue to pollute and continue to release this carbon dioxide, right? So what is the solution? That is the question, right? So this Environmental and Energy Studies Institute is very interesting, and this link will take you there. So feel free to explore around that website. So this brings us to the triple bottom line, right? So we talk about wicked problems, those problems that don't have a really clear solution. And again, we talked about the triple bottom line, which is the environment, the social, and the economic aspects of all of this, right? So for the planet, environmental, we see increases in greenhouse gases, in greenhouse gas emissions when we're burning and harvesting these coal and oil and natural gas for uses, right? It causes extensive habitat loss and changes in biodiversity, especially when we're doing this extraction in areas that are such hotspots for biodiversity, like the Appalachian Mountains. It causes water contamination. And in most cases, I would not say the possibility of water contamination. I would say it causes water contamination. It's going to happen. There's no foolproof method to stop it from happening, right? And the waste products are harmful to not only humans, but also nature altogether, from either the emissions coming from the smokestack, the coal ash that's then left over after the burning, the runoff from acid mining, and fracking water, causing our water to become flammable, right? So that's environmental. So for social, we have human health impacts for not only the human workers that are actually extracting these sources of energy, but also the communities that live close to those mining sites, right? Spills and other accidents can lead to loss of community infrastructure, and they can destroy culturally relevant natural places that exist. For economic, this is a non-renewable and finite resource, right? So we're not going to get it back once we get it gone, right? It's not feasible on the human lifetime scale. Locally, it can provide jobs and boost the economies, but the benefits are subject to boom and bust cycles. So if you're interested in coal mining, look up the history of coal mining and how certain towns were really rich, then they were poor, rich, poor, rich, poor, right? So there's that boom and bust cycle. So it's not a consistent increase in local economies. It requires ongoing technology development as we need access to harder to mine resources, right? So we're talking about the tar sands and how we cannot extract it right now because we don't have the right technology to do that efficiently. So we don't pay for the true cost of fossil fuels at the pump, right? The true costs are distributed unevenly throughout our society. If we actually paid the true cost for oil, the economic cost, the social cost, and the environmental costs, we would all be riding a bicycle every single day, right? Because these things are, a lot of these things are invaluable. Having fresh drinking water, cannot put a value on it. Having an actively biodiverse ecosystem that function, we cannot put a price on it, right? So the triple bottom line is that, you know, coal and fossil fuels are not the answer for the future, right? And so we need to start thinking about what is the answer for the future. So I had this map here that just shows you the CO2 emissions from 2000 through 2021 in emerging economies. So here on the left, so we have China in the light blue and India in the dark blue. So China, as of 2021, was emitting about 12 gigatons of CO2 per year, and India was just slightly above 2 gigatons. So then if we look at advanced economies over that same time range, you can start to see that either they're remaining the same in the case of Japan, which is just above 1 gigaton of carbon dioxide, but the European Union and the United States are decreasing their emissions, which is great news, right? You can see that really big decrease here with COVID. So you can actually clearly see the decrease in COVID. And in fact, all countries had a decrease in CO2 emissions with COVID besides China. You can see China did not have a decrease. Even India had a small decrease. But if you think about this, you can see that those advanced economies were trying to reduce our carbon dioxide, but those emerging economies, those developing economies, are still increasing, right? And so can we decrease enough in our advanced economies to offset those emerging economies? Probably not, but it's something interesting to start thinking about. So I have this question here that I'd also like you to give some thought to is, what can North Carolina do to reduce its energy usage, right? So give some thought to that. So we can't ask questions today, but I do want to have you send me a message through Canvas that gives me the answer to this poll question. So what can we do to reduce energy usage in North Carolina? So send me an answer to that. And also send me the answer to this other question that's really far away. Did I pass it? Okay, send me the answer to this question. And I'll just use that as your attendance for the day. So I know you watched the video. So if you'll send me the answer to those two questions, I'll give you credit for your attendance today. All right. If you have any questions, do email me. And I'll look forward to seeing you all on Monday. Yeah, have a good weekend.